good day to you on this Tuesday, February 10th, 2026. Over here you'll see a simple equation of a curve, and in the lower left you'll see the reflection of that curve in the negative quadrant. But all that is y equals 1 over x. Very simple curve that's doubly asymptotic, and you can see the two asymptoses, the one going vertically and the one going horizontally, that those are perpendicular asymptotes. What is an asymptote? It refers to either the straight line or the curve, and the asymptosis is the relationship between those two objects. They're called in geometry. The object that is the straight line in this orthogonal relationship is called an axis. You may know all this, but this is simply to introduce light speed, which is depicted here on this graph. This graph shows two kinds of number. One is labeled y, and that is in fact mislabeled. You can see that the equation is imbalanced, that y equals 1 over x. Why does it show a symmetry in the upper quadrant? The symmetry is around the point 1, 1, which is a bona fide number in that space. One proportion 1 would be 1 over 1, and the curve intersects the 1, 1 point. The 1 over x is a strange looking beast, isn't it? That's not a number. That's a relationship. So if you're going to balance this, all you have to do is add a 1 on the left side of the equation, and then it's perfect. Y over 1 equals 1 over x. That has a name. They're called reciprocal numbers, and the relationship has a name, reciprocity. So that's the relationship between y and x, that as those two numbers relate to the number 1, their reciprocal relationship based on the number 1 is the definition of that curve, which defines two infinities. Okay. Now, before we leave this diagram, I want you to guess, where is light speed? I will give away the answer because a quiz is meant to give away the answer. One gives the quiz, at least in my systematic approach to science presentation, you give the quiz rapidly in order to stimulate that amount of thought. It's really up to the respondent whether you care to indulge in that invitation, but that's what a quiz is. It's very important to give the answer. And so a test is cruel. An exam is an act of cruelty. I leave that for your homework to decide if that's a reasonable statement or not. It could be taken in two ways. So y over 1 equals 1 over x. That can be written without using the fractional line. And the way you write this without the use of fractions, which in this case expanding it correctly to make it a 2 by 2 matrix, you have the number 1 on both sides, but they're on different sides of that little line. So y over 1 equals 1 over x is the right way to write this. And then they're in the same 2D space. Y is not in 2D space, it's in 1D space. So this is equating, the way it's written, a 1D number with a 2D number. And now I'm going to prove to you that that's a tremendous insight into mathematics, because we're defining multiplicative space now. And this is the simplest definition of multiplicative space, except for the circle. And you can see a circle can be inscribed between these two asymptotic curves that reflect around 0, 0. So In this curve, there are two very special numbers, except that one of them is a linear number and the other one is a real number. Only it's not the conventional use of the word real in mathematics. That refers to something actually quite unreal, but we're not using the word real in that strange inverted sense of a typical real number as you commonly hear. This is a real number. So a real number on the plane must have two components. And that's what this equation proves when you add the necessary 1 to balance the equation. And then it's y proportion 1 equals 1 proportion x. And you can see that that is anti-commutative. It's anti-commutation defined. So the y over 1 is one aspect of a relationship where if you invert the system so that you have 1 over y equals x over 1, I leave it to you to figure out what that curve would look like, although we can work it out now and probably should. But the reason I wanted to show you this is because light speed is a two-component number. It is a fraction. And you can see that 1 over x is a fraction. As I've taught you to say, and I just want to remind you, and this may be the first time you hear this, do not say fraction, because there's a better word. It's a proportion. And a proportion is non-commutative because it's proportionalizing to quantities. In light speed, the two quantities that are being proportionalized into what is commonly called a fraction, but is strictly speaking a proportion, which can be written as a fraction. That's perfectly legal. Why do I take such umbrage at the word fraction? It's because it implies linear division. But that's not what this is. It's not linear division. It's circular proportionality. And it is circular, and that's why this is a curve. That curve can be transmuted into a circle. However, it's very interesting how that would be done. That's deep geometry, and I'm not going to go into that now because this is a much simpler approach to what we're after, which is the surface value that defines a supermassive black hole, which has recently been proved to have a surface, which then is a spherical surface. So it's very similar to a proton, which also has a spherical surface. And these are, respectively, the smallest spherical surface known to man and the greatest spherical surface thus far discovered. So a spherical surface exists that defines an SMBH, and it is the same spherical surface that defines a proton force field. So a protonic force field is what is responsible for what is construed to be space bending. If indeed space can be said to bend, and it certainly is in space-time, it's for that reason. So what we're doing now is correlating what we've already discovered about spherical geometry such that it has a multiplicative space basis. And when you use the subset of the linear numbers called the binary numbers, which are construed as the linearizable two-component numbers, that's what binary numbers are. They're representable linear numbers, but they're not in linear form. They're all in fractional form, beginning at 2 over 1. So 1 over 1 is the center of the binary system, and strictly speaking, there's no number less than 1. You would object immediately, I certainly would. What about the numbers less than 1? They're certainly there, but does it go to 0? No, it can't. Obviously not, because the center of the system is 1. So when you say there are no numbers less than 1, what you're actually saying, there are no negative numbers. I'll now show you that linear negativity, that is the negative linear numbers, are captured on the power line. And for that, we're going to need one more diagram. Here is our now rather familiar simple diagram of a spheric surface. Now that may not look like a spheric surface, but just think of it as the moon. Now in this case, what we're doing is looking at the moon from an eigenaxis, which is unique to every sphere. Every sphere has one and only one eigenaxis, and that's the axis of rotation. And the eigenaxis is dual with the equator. So the equator is the integral of rotation. As I've been suggesting strongly, we're now going to prove that. And this will lead us into the definition of light speed. You are essentially looking at the definition of light speed. A light speed number is a planar number. It refers to a plane. So light speed refers to a plane. How so? It's because there's motion. And you can't have both distance and motion in any space less than 2D, because you need one of the axes to represent distance, and you need the other axis to represent motion. That's exactly what light speed is. It's the relationship between a quantity of time and a quantity of space. And the exact relationship will depend on the units chosen for each domain. These are two separate domains that have been unified in space-time. They are both linearized quantities. The space quantity is a 3D quantity, which is simply a linear quantity. The time quantity is linear. It's a linearized quantity. So in the space-time system, time is linear. It is said to curve, and space-time is said to curve. And that's an interesting thing to say. What you must say, because the whole system is premised on some form of sphericity, is that something is linearized and they are related to each other, that is time and space, such that both can be conceived as curving in coordination. And that is a relationship that has a mathematical representation in units of time, which is on the bottom, called the denominator, and the units of distance, which are on the top. That's linear spatial separation. That is a linear number. So it is a distance over time. And it's a 3D distance which can be computed using the Pythagorean theorem. And that's how Einstein did it. He used the Pythagorean theorem on four summed quantities. The strange thing about the time quantity is, first of all, there are two things strange about it right out the gate. The three spatial dimensions have to be positive because distance is positive. That's called Euclidean geometry. The time component cannot be signed positively, so it has the negative valence with respect to space. In some sense, it is going in the opposite direction than space. That would, if it's conjugated with space, bend space, because now it has a component that bends it. But it doesn't actually bend it if you make time positive. Then all you have is a hypercubic space. What Einstein was forced to do for a couple of reasons was to sign time negatively, so that to the proportion that space is conceived as having linear positive valence, which it is, to that proportion, time cannot be considered to be going in the same positive directed orientation, which is a orientation. But how is it oriented differently from space, since we can only conceive of space as going out from an origin positively? There's no such thing as negative space when it's being measured as a distance. It's a positive quantity. It's not a negative quantity. So why would linearized time, and it is simply, I'm just being a little bit redundant, but it's important to spell this out here. It's linearized. It's a linearized quantity. Now that's actually suggesting something that's not necessarily true. What am I suggesting? That it's not actually linear. Is time linear? In the Einstein field equation, it is. It has to be. Or it could not be perpendicular with the three spatial dimensions. But if it is perpendicular, as it is constructed to be, it has to be oriented with a negative sign such that it is polaric opposite of any of the spatial dimensions. It's actually going in the opposite direction of all three space dimensions combined, which means it's going in instead of out. That's one way of saying it. It's a little bit strange to say. How can time be considered going in when space is going out? If indeed that's the right way to characterize it. It's actually not the right way to characterize it, and that's what I'll be showing you. This involves the conjugation of two infinities so that we can establish the boundary of physical space. This is the first so far concerted, coherent attempt to actually finitize the physical universe based on what we already know. Is the universe finite? There are several ways of answering that. The answer that I am now capable of giving that no one else can give is a series of powerful answers, all of which are true. So we'll just list what I can now say about the geometry of the universe. The first question is it spatially infinite? There are two ways of answering that, and that's actually the paradox. Is the universe spatially infinite? What we have been looking for now with the James Webb Telescope, but the Hubble Telescope preceded that, and this has been going on for about a century now, since the universe of galaxies was discovered a century ago. We're trying to decide, once and for all, is the universe finite? The Big Bang actually suggests that it is, but it's a very interesting form of finiteness that, as you know, originates in essentially a Euclidean point. That has been challenged, and successfully, actually by Neil Turok and his team. Their first discovery using their geometric insight into the Einstein field equation for gravity is that in their exploration of how the Big Bang is constructed mathematically, which it is a mathematical construction, he discovered that Big Bang cannot be the Euclidean origin, that it is construed to be necessarily with a Euclidean equation. And the equation of the cosmological constant, the cosmological principle, the principle of cosmological expansion from the Big Bang explosion, however that explosion be construed, it would be reducible to a Euclidean singularity, which is the center number, technically non-existent, 0. So that would be the current mathematized origin of the universe, is a Euclidean reference frame 0, which means that it's a point. So the universe originated as a point. What the Turok team proved is that the Einstein field equation does not prove that. It suggests that as a possible linear solution, which is exactly how we got cosmological expansion and the cosmological constant, which, let me remind you, Einstein was mortally confused about. Enough so that he said, and this is famous, he said it was the greatest mistake of his life. But I leave it to you for homework. What did he mean by that? What was his greatest mistake? Putting in the cosmological constant into the EFE, the most famous equation of all time in physics, or, unless it's E equals mc squared, and that could be argued, it's a beauty pageant contest, But certainly the Einstein field equation for spacetime is considered to be the bedrock of physical science now. Is that proper? Well, that's what science is always addressing. Are we getting it right? Well, if you're saying that the universe originated at a Euclidean point, Neil Turok and his team say not necessarily, and in fact they can prove that the Einstein field equation does not actually even suggest that. It's a derivative solution of what the Turok team discovered, which is an integral solution, which of course is much superior. That's why we have calculus. So this is a direct insight into the nature of the supermassive black hole, which the Turok team have correctly defined as the singularity. And it's a specific kind of singularity. A singularity is a fail point where mathematics ends and so does physics. So you don't want singularities, it's a kind of infinity. But it's a strange kind of infinity because it's an infinity you can plot. That is, you can localize it. So how can an infinity be localizable? It's if it doesn't have a center. And that's what he discovered. The singularity is exactly that surface at which regular physics ends. So the question is, what is inside, because it is finite. The supermassive black hole does not consume the whole universe. It's localized in space. So what is inside it? Well, it's what's inside the singularity, which is the surface, where everything reverses. The question is, what is the nature of the reversal? That has led to some rather psychotic, and this may remind you of the quantum mechanical phantasmagoria of what is meant by physics ends. What does it mean when your mathematics cracks? What happens when your numbers don't perform? What happens when you have a system error? What happens when your computer halts? What have you done? You've used the wrong number system and your mistake was inevitable. What's the mistake? Well, Neil Turok has been able to show that one way to approach the error is to see that the construction of the singularity, which is called by a specific name, is a certain kind of singularity. It's called, and wait for it, this is a bona fide term you can look up, it is a curvature singularity. A curvature singularity. Well, over here you see the perfect curve. It's called a sphere, and that's a 2D projection of a sphere. You're looking down the axis of rotation, and therefore the equator is the surface. It's at the surface of that sphere. It's called the eigenCircle of the sphere, and that leads us into our definition of light speed. How can this simple diagram be showing us light speed? First of all, light speed is not a linear number, but it is composed of two linear quantities, one of which is in units of linear spatial separation called distance. That's always positive. So it's positive distance over time. Time has to be quantized. It has to be unitized. Is that reasonable to do? To make this work, yes. And then the calculus does the rest. That's quite an interesting process, by the way, getting down to Christoffel symbols and gamma symbols and an involute form of calculus that Einstein basically invented for his purpose. It is consistent with the principles of standard calculus, but it is not what anyone would call regular calculus. It can only be computable with a supercomputer. And you may notice that supercomputers essentially came online at the exact same time as space travel. And Einstein arrived just in time to invent the special relativity and general relativity conversions for a GPS system, a satellitic system, in order to coordinate time through relativistic effect. And that enables space travel. And without those corrections for special and general relativity, which we won't go into specifically here, but this is how you navigate space probes. And without those conversions, because there's always a time lag through space, you have to be able to compute that. You will need supercomputers to do that. And that's what's done. And that works. I would call that nothing short of a miracle. But it's quite an interesting miracle because certainly the military, which you could just say is an arm of the government, the military was vastly interested in that. Because with those GPS networks above the clouds, you can guide missiles to destroy the lives of your enemies. And that's what relativity is for. It's for the military. But that's not all it's for. It's not just for initiating doomsday. That would be rather self-defeating in a logical sense. There must be some reason that these secrets are being exposed to the universe. Well, in the latest Kurt Jai-Mungal science presentation on his award-winning station, he just interviewed a Russian physicist and mathematician who's currently at the cutting edge of all this stuff and getting quite a bit of attention. He's extremely cogent. And I think I like this guy. I just started watching the 2.5-hour video, if I recall correctly. This guy is entrancing. And of course, he's following in my footsteps. But he's doing so along a very interesting line. The geometry of the learning neural network. That's a little bit redundant, but I'm adding the word learning to emphasize. That's what he's a pro on, is how computers learn. And his thesis is the universe is learning from us. I have something to add to that science fiction scenario. It's not the universe that's learning from us. It's another entity inside the universe that just happens to be coextensive with Earth in some way, which is something you literally, and I'm just going to warn you, you do not want to know anything more about that, because that's what's destroying the Earth. And that's really a downer. It's just so sad for all the puppies who will die along with everybody else very, very soon. So that's where all this leads. And you could say, well, God curse, heaven smite. You just get all defensive. Save the earth. Who's destroying the earth? Stop them. No, you do not want to do that. You can't stop it. It's not them, it's it. And it is going to do what it intended to do, and it's doing it. And that's in prophecy. If you care, I don't know why you would. It's bad news. It's the worst news you'll ever hear. No more conspiracy theories. That's all done with, darling. It's happening right now. You can't cross into Iranian airspace without initiating the Armageddon. Russia is on full alert right now. This could be it. China is just eyeballing this because they know that they're going to win. They're just waiting to see when they can strike. And that may be sooner than any of us want. Sooner than any of us wants. So back to our topic of light speed. This does have to do with cracking the secrets of the universe, so this is really turbid waters. Not for us. We're pure scientists. We only want to know the truth. These are the crumbs that fall from the master's table. You don't want to know who the master is in this situation. It's pretty ugly. It does involve genocide and, of course, the continuation of eternal warfare. Men killing other men. What a story. What an amazing time to live. I've heard other men say this, but I'm going to chime in. There is no better time for a man to be alive than right now. But only if you pay attention right now, because I'm going to give you the answers that all of your physicists are seeking, perhaps even on the good side of the force. I would put Neil there. Certainly Kurtjai Mungal is trying in that direction. Well, I've got the answers for all of my friends. And you're going to hear it right now. What is light speed? It's a two-component number that you can plot in circular space. You're looking at it. Where is light speed there? Well, how do you define it? It's a two-component number. So it is a relationship between a certain number of seconds. And here you would probably raise your hand. This is the right time to raise a brawl. Start rolling up spitballs. What do you mean by second? What the hell is a second? It's an arbitrary unit of time. That's the key word. It's arbitrary. We just assume that a second exists. It certainly can be proved that it does as well as any other unit of time, but that unit could be of any duration, and you just make that the unit. Well, we've decided on the second because it's a traditional division of circular time. Circular? Well, yeah. It's based on a year. Well, what's a year? It's the time that the Earth goes around the sun on a circle. So that's a year, and that defines a second. By simple division, you can divide out what is a second. That is what a second is. It's now more accurately approximatized with a cesium clock, and there are other ways of doing that, including using the pulsar. The millisecond pulsars are excellent timekeepers that rival the atomic clocks. But in the GPS system, they are, I believe, cesium atomic clocks, using a fine structure constant oscillation, I guess you'd have to say. It's very well computable, and so we keep very accurate time, but that's what it is. It's the amount of time that the Earth goes around the sun once. As you could probably guess, that's variable. It certainly is, and so there's a list of, last I counted, about 32 independent variables that goes into computing solar system time, which is where we get the second. Is that the proper unit? No. No, under no circumstances will the second satisfy our needs. What we want is Planck time. We want the Planck unit of time. What's that? That's actually known. It's a value in certain units, which would have to be carefully defined. The base unit of time, well, it's currently the second. But what do we mean by that? It's currently defined on the fine structure constant in a certain oscillatory relationship within a certain kind of atom, specifically part of that atom, where a measurable change occurs in the state of the atom, essentially, which is so natural, it keeps perfect time. So if you wish to know more about that, that is quite a story, but we can't go into that here. But that's how a second is measured. It's measurable. And what is the smallest unit? That would be the Planck unit. What is that? In the base units, which we may or may not want to define, it's 10 to the negative 44th power. It's less than the Planck length, but really, this is a matter of relativity. Pardon the use of that overworked word, but it is actually relative to what you mean. Are space and time combinable? Well, Albert Einstein certainly proved there's a linear solution that shows that they're related mathematically, or this wouldn't work. There wouldn't be spaceflight. There wouldn't be a GPS system if relativity were untrue, so it's definitely been proved. Well, you'd have to say to a certain threshold. Well, you always have to say that in science. So what is light speed? It's approximately, currently as it's defined in the proper international units accepted by all top physicists, the definition of light speed is 299 million. What units are we using? Meters. That's the distance is a meter. This is about the same as an American yard. It's a little bit more, I think. I'm not sure. I actually don't care. But because we're going to change the units to Planck units. But first you have to know what we're changing. Well, the current metric for linear spatial separation is the old French meter, a very useful. It's arbitrary, though. You can use anything as your length. Well, the meter turns out to be something we can visualize anyway. A man is somewhat under 2 meters tall. So that's the unit. So, how many meters per second is the definition of light speed? How many meters per second? So it's about 290, well, it's now exact. It's been exactified, which is an interesting thing to do. This was made precise in the 1960s by decree. And you could argue with that or not argue with it, but it's a done deal now because scientists need to agree to a certain level of precision what is meant by a second. Well, this is how they do it. It's in conjunction with the relation of time in seconds to distance in meters. So those are the units that are being related, meters and seconds. And if you make the number of seconds 1, which is called unitizing the domain, there are other terms that use some variation of the word unity or unitarity or unitization or unit something, you make it 1. You arbitrarily state that your counting unit really can be called the metric unit of what it is you're trying to measure. Well, in space, it's distance. So that's a meter. So how many meters of distance relates to a unit of time, which we will say is 1 unit called a second. So that's what is meant by over 1 second, per second, per second. So that's a proportion. It's the proportion of linear spatial separation covered per unit of time. And that's called unitization of the time metric. This is a combinative metric called spacetime. So light speed is defined in spacetime numbers. The top number is space, the bottom number is unitized time. That's where we get our 1, and so you can write that as a fraction. And as I just showed you, that is a 2-component number, which means it's a planar number. You can plot it on a plane, and it is a linear relationship. If you plot the relationship between distance and time, it's a linear relationship, which means on a Cartesian graph, it's a straight line relationship. In the projection of space-time down to a 3D'able 2D image, you get the light cone, which is very interestingly defined as dividing the entire geometric field, which is representing space-time itself, is only inside the cone. And what is outside the cone, which is exactly, I believe, yes, it would be exactly half of the entire volume of space-time, is undefined. It's undefined. So that's the part that's dropped when you add a 4th orthogonal vector to space and it's negative. You have the hypervolume space, such that only what is inside the cone, in either direction, going time forward, which is the unfolding cone of reality, or the reflection, this has to do with Turok's work, as you can now guess, is anti-time. It's the past, which can be plotted as the reflection of the future. The past does exist in some sense, because it's what's left behind as we acquire the future. The boundary between reality and unreality, the cone itself, which is a boundary between non-defined anything and the space-time volume, going up it's a cone, which you can just disregard the reflection for now, since in reality we only go forward. Whether or not there's any realism in the backwards reflection is a matter of what Neil Turok actually has something quite cogent to say about, and I can support his work. But that would imply time reversal from our perspective. That's not the right way to look at it, but you could. And people like that because it sounds like science fiction. I'm certainly vitally attracted to that myself, but you want to remain rational at all times in science. And that's not quite rational. But there is something that there is certainly a reflection around that surface. The surface is the light cone itself, which represents the speed of light. It is light. So the universe is bounded by light in this attempt to diagrammatize or make visible the pseudo-geometry of space-time, which can be plotted inside that cone, which is at a 45-degree angle to origin on a circular expansion, which you see over here in this diagram. Those three concentric circles are the increasing radius of a space-time expansion. But you do have to have time, and time is nowhere visibly here because nothing's moving. If you saw it moving, it would be expanding. Why would it be expanding? Because you're plotting the flight of a photon. The flight of a photon begins at 0. It is plotted that way. I'm afraid there's no getting around the 0, and that's the quantum paradox, is that transition from 0 to reality. So the photon begins at a Euclidean origin of 0, 0, 0, 0. Okay, that's correct. That's a space-time coordinate, and that's the focus of the cone. So that's called now, and that's called here. So that's a highly abstract representation of essentially a point of consciousness. Definitely, you could say so. So the point of consciousness is the reference frame. It's the frame of reference for the system. That's the 0 at the point of the cone. That would be, in time terms, now. And now when you start the system, it now moves on a linear trajectory upwards. And that's the opening of the light cone. That is the path of the photon from the origin is on that cone. That cone is a photon projected into the future. And what's inside the photon cone in this projection is space. So that's an interesting way of looking at the light cone. And it's very difficult, I think, for the human mind to understand that is showing you the curvature of space. But when you plot the actual way that the Minkowski system is used to parameterize that system with basically space-time coordinates, you get a super hyperbolic projection, which is extremely difficult to visualize. Although it can be done on a learned inversion. So, we're not going to go that deeply into the geometry of linearized curvature, which is what it is. We're going to look at the curvature itself using a brand new geometry called intrinsic geometry, which, strangely enough, has its own number system. You can actually see that on this diagram, and the way we get light speed from this diagram is recognizing that that is the flight of a photon. And the spokes going out represent the speed. That's the speed of the photon going out in all directions. So that's the integral of speed. And so the integral of speed is on the surface somehow. Is it the spokes or is it the surface? Those are perpendicular. The pressure line going out, which is what makes the photon go at its speed, it's not fired out of a cannon, so it's not Newtonian speed. its inertial speed in its reference frame. It's falling. The photon falls through space, and it falls in all directions at the same time. Quite a mouthful. So the photon is an expanding sphere. That's been known for 4 centuries. Nobody argues with that. It's a spherical wavefront. But if you compose a single photon, and this is quite artificial, but if you have a photon that just appears out of nowhere and starts to expand, which is almost true, it follows this circularized spherical expansion. It's expanding as a sphere in space. Why is it going at that speed? It's not because of innate Newtonian force. So you have to account for its speed somehow, but how are you going to account for that exact speed? Why does a photon always travel at that speed given optimal conditions, which is nothing in its way? Why does a photon go at that speed? Well, it is distance over time, so it is a 2-component number, so it should be able to be plotted on a plane. Because it's a planar number, it has 2 components. So you can plot time either as x or y, and you can plot space as y or x. And when you combine them, you will have space-time. Well, if you can put that on a circle, you have the angular momentum. Would that generate that speed? No. And this is where it gets very interesting, because how do we even know the speed of light? How do we know that? Do you know the proof? There's a very good Veritasium presentation. That's a channel on YouTube. Veritasium. Veritasium. And he has a very well worth seeing video presentation of what it takes to measure light speed. And the theme of that video, again, I highly recommend that video because I can't go into all the details here on what that means about light speed, but you can't measure it in one direction only. And you may not know if that's true or false. I still stutter at this, but that video, which I've watched twice and I think I'll watch it a 3rd time, shows you that the only way to be certain that you've gotten light speed is on a reflection. Very worth seeing. So, light speed is a very interesting relational quantity. It's a proportion, not a linear number. It's the relationship between 2 linear quantities. So, are you correctly deriving the linear quantities? No. In the Einstein field equation system, both quantities are already linearized. In the signature, they're linearized as linear numbers. So the 3 spatial dimensions each are linear, which means they have a 0 reference frame. I just proved to you in the past couple of videos that you cannot use a linear reference frame for physical space, because there's no such thing as 0 in the universal number system, which the lowest number in the universe is 1. And you see it, it's the outermost circle, which would be representative of what? We're going to show now that since that's the eigen of the sphere, that circle has a surface value of 1, it's actually 1 over 1, which is best written and thought of as 1 proportion 1, which you can write 1:1. That's a little bit non-standard. Almost everybody writes it 1 over 1. That's okay, but just don't confuse that with linear division, okay? Because that's not what is going on with those 2 numbers. In the binary number system, those are both quantities, which means they're counters. So there is no 0 because 0 is not a counter. The center of the system here in binary space, which is 2-component linear number space, they're 2 linear numbers combined into a new form of number called a fraction. And as we carefully showed, the balance is no longer linear 0, it's circular 1, which on the plane has to be 1 proportion 1 to capture the 2 linear dimensions in a perfect rate. And that is what light speed is. It's a rate. You have to say rate because time is involved. And time has a very interesting data type that's non-spatial. So how do you correlate the linearizability of the time component in spacetime with the naturally positive 3D linear systematic volume space? How are those orthogonal? I'll be able to show you that now. They're spherically orthogonal. And Einstein was able to deduce that in the derivative, the time component, which is actually, as I'll show you, a derivative of energy, that linearized quantity is perpendicular to already linearized volume space. 3D is linearized space. It's an extrinsic geometry of a grid. It's a cubic grid. He made it hypercubic, but then it would be strictly hypercubic if time were positive. But it can't be positive because then you can't capture what you want to capture in curvature. You would simply get a tesseract, and you can look that up. That's actually in A Wrinkle in Time. The tesseract is a bona fide mathematical term, actually a geometry term, for a hypercube. What we're going to be discovering is hypersphericity, which is much more accurate. In fact, it solves the quantum paradox and the mystery of the supermassive black hole curvature singularity, all of which are precision terms. So here, to get light speed, what you need to realize is that you need to unitize light speed. And that's commonly done in upper echelon mathematical physics. Instead of unitizing just the time component, you unitize the quantity, which is a rate. So you make the rate 1 proportion 1. That's the definition of this circle. The definition of this circle is light speed, when light speed is unitized. Does that help us in some way? Yes. And here, I'm just going to utilize the fact that there are conveniently drawn here 3 concentric circles, the innermost one of which is red. We're going to say, since that is labeled 1, that that has the value of the circular unit circle, which does not have a radius of 1. It has a surface value of 1 proportion 1. So that should make sense. That's the perfect rate. And a rate is a calculus derivative, which means that you're looking at the integration of the derivative so that they are reciprocal. So the surface of a photon, which is what that red circle is, that is light speed. So the photon obviously manifests light speed. You can compute that from the circle geometry, which has 2 components, one of which is time and the other of which is space. You can see that the circle makes a line in space, but it's a closed line, so that's the line. The circle now replaces the line. Instead of the line going to 2 polar infinities when it's drawn to infinity, the circle does not go to an infinity. It's closed on itself. And that gives us the ability to parameterize time on the plane in the circle itself as one of the 2 components that multiply to 1. As you know, the way that you get that bifurcation of the number system into the positive and negative binary numbers, they're not negative numbers, they have negative exponents. 1/2, 1/4. Let me draw that. If this were the 1, 1 surface, if you go halfway, that's a jump halfway to the center. That's 1 over 2. If you do that exact same thing again, and now consider this middle circle to be 1, that is now 1 over 2 with respect to the outer circle. This is a jump from 1 over 1 to 1 over 2, which is less than 1, so that is less. You're going in. Then you jump to 1 over 4, and then you jump to 1 over 8. And that's exactly reciprocal with the journey to spatial infinity. So they converge simultaneously onto infinities. This infinity is the one we're interested in. That's linear 0. That does not exist. So that's an imaginary number. It's too much less than 1. It's gone to nullity. That does not exist in binary space. So this circle is the smallest number in binary space, which is 1. Now you may object. There's 1 over 2. Yes, you've jumped halfway to the center. So that's always going to be true. That's called Zeno's paradox, is that by proceeding towards the center, by jumps of half, 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 you never reach the center. That's an asymptosis to the center. That is proportional to the asymptosis going out, which gets bigger and bigger and bigger, to the proportion that its reciprocal gets smaller and smaller and smaller. But the relationship between those two numbers is always 1. It's always 1. So, if we say that this circle has a value of 1 proportion 1, we will now hypothesize that the top number, called the numerator, is the space equivalent in circular space. We will then say that the bottom number is the time equivalent in circular space, so that we have distance over time represented on the circle. Can that make sense? Get ready for the shock of your life. Take a look at the circle. How many points are on it? Well, we haven't said. We haven't put any points on the circle. Can you do so? Go ahead. The traditional way to do that is to measure on one of these lines, although it's arbitrary, and you put a point on the circle. What do you have now? Well, you don't really have much of anything except a point on the circle. It does divide it. How does it divide it? It gives a reference point. What good is that? Well, let's say you are going around on a continuous rate of about 1 second per revolution. Perhaps this is turning, which all spheres do, and you're measuring the rate of it turning. That would be on the circumference, obviously, the integral of the radial line. So that is the rotation rate. You can measure that by putting a little chirp, so that now you can measure it acoustically. So that as it makes the circuit, which is the distance component, it is consuming a certain amount of time. And that's the relationship between time and space on the circle. And so it sounds like this. Click, click, click. Replace that with the distance value. 1, 1, 1. So when you put the point on the circle, you're establishing a time reference. What if you put 2 points on the circle? Something magic happens when you put 2 points on the circle. First of all, you would want the simplest set of 2 points. These are called antipodes, and you can see that right here at the extreme south or the bottom of the circle, is 1 point, and if you follow that perfect diameter to the top, that's the second point. Now what do we have? What we have are two new quantities, one of which is the arc length on the circle, which now will be 1/2 instead of 1. But the frequency goes up to 2/1. So this is the frequency wavelength relationship projected onto the circle, which is the eigencircle of a sphere. It now has the value of energy. That is the equation of energy. It's the lowest frequency times the highest wavelength. The highest wavelength we know, it's 1/2. And the smallest frequency is 2/1. That has a different acoustic value on the same distance. Only now the distance is cut in half, but the two halves make a whole. The reference point for time is still 1 point, but now the point is divided in half. Follow along. Click, 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 click. That's twice the frequency of click, click, click. That's with 1 point for the click. With 2 points, antipodal points for the click, it doubles the frequency and halves the wavelength. The wavelength goes from 1 to 1/2 to the proportion that the frequency goes from 1/1 to 2/1. That's the definition of the binary number system. Correctly defined. There's actually several definitions depending on your approach to the binary numbers. But that is the physically correct definition of the binary numbers. So wavelength and frequency are conjugated on a unit circle, where I've changed the definition of unit circle so that the radius, which is directly computable as an irrational number, is 1/tau. That's 1/2 pi. By the way, that gets rid of the irrational constant 2 pi, which is in the Dirac equation, the Schrödinger equations, the Klein-Gordon equation, the Heisenberg equation, space-time. Everything has 2 pi in it. Everything has 2 pi in it. Not anymore. I rationalized it so that in integral space, which this is, you can see so. That's all going to be in my paper. But now you know where time exists, but you can see that time is in relation to something that is not exactly space. It's curved space. This is the relation to time in perfectly curved space. And this defines the photon, which is the quantum of energy. That has a range. The quantum of space does not have a range. The quantum of space is constant. It is called a proton. All protons are exactly the same. All electrons are quantizable. Otherwise, we couldn't measure them, right? So we do have a unit of energy. The unit of energy is a two-component number. I just told you what it is. It is 1/2 times 2/1. When you reduce that to the actual surface, it's 1/1 proportion 1/1. That is hyperspheric space. And now we enter super science fiction, where I will get a much better answer than Neil Turok's team did with their linear reformulation of the Einstein field equation for the supermassive black hole curvature singularity, which is redundant. And we're going to find out for the first time what's inside an SMBH, because now you can see it. Get ready for the next video. I wish thousands of people could hear what I'm about to say later today, I project, where I give you pretty much everything that physics wants to know all the way. Grandiose, perhaps megalomaniac, you try it. You'll find out. It's going to be profound, whatever it is, because it's got to be simple and beautiful. It is. Keep looking up. We'll be right back. Thank you so much.